Alright, hello everybody. Welcome to the first lab of Anatomy and Physiology 2, where we're going to be primarily focusing on the endocrine system. I got two different PowerPoints and a Word document that I'm kind of going to be bouncing back and forth between. So let's get right into it. The endocrine lab. Let's see. Go ahead and flip that presenter view and then go ahead and give me a laser pointer. Much nicer. Okay, here we go. Hopefully you guys remember from Bio 210, we talked about four main tissue types. We talked about epithelial tissue, muscle tissue, nervous, as well as connective tissue. So in the endocrine system, we're actually going to be focusing a lot on the epithelial tissue again, and then a little bit of the nervous tissue. So for the epithelium, we talked a lot about, simple columnar and simple cuboidal and all these kind of secretions and absorptions that our cells are capable of in the epithelium. Now, what we're going to be doing with the endocrine system is we're going to be doing a lot of secretion. And what exactly are we secreting? We're secreting hormones. These hormones are going to dictate a lot of bodily functions. There is a small portion of the nervous system that is also involved in the endocrine system, and I'll be sure to point that out to you guys as we go along. So, introduction to the endocrine system. It's basically in charge of regulating long-term processes. So this includes growth, development, as well as reproduction. So this is actually very distinct from the nervous system. The nervous system is a very quick, very short kind of way of enacting various responses in the body. However, on the other hand, these hormones are actually going to control long-term processes that have to last much longer than like a second that a nervous system or a neuron signal would last. So this is the essential mechanism of how the circulating hormones is going to work, as opposed to paracrine and autocrine. These should also look familiar. Auto refers to self, so autocrine refers to the cell giving itself hormones. So you can see these green little Y-shaped molecules sticking out. These are our receptors of the molecules. And these little black balls are essentially the products that the cell is producing. So autocrine produces a product, goes back onto the sensor of the cell on itself. The paracrine cell is actually going to be in the general area. Para means around, so these products are secreted to cells that are nearby. And then finally we have endocrine cells. So endocrine cells are actually known as circulating hormones, which means that they're going to enter the bloodstream and going to go to very far distant target cells. So we're going to kind of point out the various organs that we have on the body, and we're going to also kind of look at how these hormones circulate throughout the entire system. So first up, we have a feedback mechanisms. We have two different types of feedback mechanisms. This should also sound, fairly familiar from your previous experience in anatomy and physiology. We have negative and positive feedback mechanisms. So negative feedback refers to the fact that a product is going to inhibit an earlier process. So what this means in general is right here, let's kind of run through this example. We have cold exposure. Our body recognizes, oh, it's very cold outside. So that kind of communication is going to go up to our hypothalamus. We'll get into what our hypothalamus and our anterior pituitary is in just a minute, but for now, it goes to our hypothalamus. Hypothalamus says, release the thyrotropin releasing hormone, and then it goes to stimulates the anterior pituitary, goes down to the thyroid. Thyroid produces a hormone that's going to warm us up, because that's the original problem. Right? The original problem is we are cold, so our solution is to warm up. Now, once this product is created and our body starts to warm up, this same exact product that has its function to warm us up is also going to tell the previous essential organ that, okay, we're good, we do not need anymore. Now, the reason why this is occurring is because if we didn't have this negative feedback mechanism, we would just continuously keep producing this product, and then we would have a whole nother issue on our hand where we would be too warm instead. So this is why negative feedback is extremely important. Please make sure you understand this concept, because this is a huge concept for biochemistry, going over the Krebs cycle and glycolysis, all kinds of stuff. It feels like you're constantly learning about the feedback mechanism, or the negative feedback mechanism. On the other hand, we have a positive feedback mechanism. So if our negative feedback system was to stop something, our positive feedback system is actually going to encourage it. And there's two primary examples that are used most often. The first being childbirth, and the second being actually blood clotting. So let's go ahead and focus on the childbirth example instead. So right here we have child. Child is growing. Eventually, the child's head begins to push against the cervix. The fetus's head begins to push against the cervix. This stretch sends an impulse to the brain. The brain's going to stimulate the pituitary gland. And it's going to say, okay, let's release some oxytocin. The oxytocin gets carried down into the bloodstream to the uterus, and the oxytocin is actually going to stimulate the uterine contraction to kind of create more propulsion so that the baby's head hits it again. So essentially, as the baby's head continues to push, more oxytocin comes in, the baby pushes more, which causes more oxytocin to produce, and so on and so forth. So you can kind of see how this is different from the negative feedback where we're stopping something, and then positive feedback is actually pushing it forward, like it's going to keep it moving. And this is actually how labor is produced. So once a woman is going into labor and she has to start pushing, this is actually the process that it's used in order to slip the baby on out. All right, so taking a look here, we have a lot of different glands, just organs in general that actually produce a number of different hormones. And we're going to kind of break down each of these glands and hormones one at a time as we kind of move forward. Hypothalamus. So the hypothalamus is incredibly important. Hopefully you guys were introduced to this in a little bit in Bio 210. You guys were probably told that the hypothalamus is essential for maintaining homeostasis. And while that is true, you are now going to go into more detail about how the hypothalamus is actually in control of this. So a general rule of thumb is that the hypothalamus is in control of the 4 F's. Now, the 4 F's include feeding, fighting, flighting, as well as sexual reproduction. So that's a good, easy way to remember the functions of the hypothalamus. The hypothalamus is prone to producing and secreting, releasing, as well as inhibiting hormones. So it's going to release 2 different types of hormones, releasing and inhibiting. Releasing is obviously going to stimulate the production further down the line, while inhibiting is going to stop the production of a hormone further down the line. Now let's go ahead and take a look. This is the general region our hypothalamus is located. And our hypothalamus is actually located directly to our pituitary gland. It's this little small sac-like structure that's actually hanging out down at the end. This is our pituitary gland. Hypothalamus is connected to the pituitary gland directly. So the pituitary gland is also referred to as the hypophysis, and it lies within the sella turcica of the sphenoid bone. Now, in order to understand the relationship between the hypothalamus and the pituitary gland is to kind of think of this in a work life scenario. So if I can go ahead and get my pen, here we go. So if we're looking at this, the hypothalamus is essentially the CEO. That's the Chief Executive Officer. CEO is in charge of the entire company. He is the one that ultimately decides what direction the company is going to go into. On the other hand, the pituitary gland down here, you can see it's split into an anterior and a posterior, and we'll kind of get into that in a little bit. The anterior and posterior pituitary gland work together as just the hypophysis. This is, you can think of these guys as the GM, or the general manager. Now, the CEO has a lot on his plate, right? So he cannot talk to the workers individually. However, the general manager can. The general manager is going to be the one that's giving direct orders to the workers, or in this case, the various endocrine organs throughout our body, like our thyroid gland, our parathyroid gland, our kidneys, and so on and so forth. So that's honestly the best way to kind of think of this relationship of hypothalamus and pituitary gland, is the difference between a CEO and the general manager. Now, We have two distinct regions of the pituitary gland. We have the anterior lobe, which is known as the adenohypophysis, which is in charge of releasing and inhibiting hormones. And then the posterior lobe of the pituitary gland, also called the neurohypophysis. Now, you might be wondering, okay, what's the difference between these two terms right here? So the reason why we call the posterior lobe the neurohypophysis is because the posterior lobe of the pituitary gland is connected to the hypothalamus directly through neuronal activity. So neurons, we can actually see it back here, neurons are actually exiting from the hypothalamus and entering the posterior pituitary gland. There are two specific hormones that are actually secreted from the posterior lobe. That's going to be ADH as well as oxytocin. So this is actually pretty interesting, the difference between ADH and oxytocin. The reason why these two glands, I'm just going to stop it right there because this is making it a mess. The difference between ADH and oxytocin and the difference between them and the rest of the hormones is that ADH and oxytocin are directly connected to memory. So there are certain events in our lives that actually require ADH and oxytocin to be produced that actually can alter memory, or they're directly linked to memory. So if your body's undergoing a specific process, it's like, in this case, I'll use the example of oxytocin. So oxytocin is that hormone we talked about earlier with the child. So you can kind of think of it as in when women give birth, it is a very painful process, right? But oxytocin is essentially that love hormone. So it's actually what makes it worthwhile. Otherwise, I doubt anybody would want to go through any kind of pain like that. And oxytocin is also responsible for altering the memories of pregnancy so that, you don't remember it being as bad as it was. So that's just a kind of, just a dip into like how the neurohypophysis is a little different. The adenohypophysis is actually going to be connected through a blood circulatory system instead. So let's kind of keep moving on. Adenohypophysis, neurohypophysis, talked about those. Okay, perfect. So getting into the portal system. So this entire network is known as the hypophyseal portal system, right along here. So the hypophyseal portal system is how we're going to connect the anterior lobe and the hypothalamus. You might be wondering, okay, well, how exactly does that work? So very briefly, I'm going to go down here and I'm going to create a slightly different scenario just to kind of introduce you guys to the idea of a portal system. So in general, in anatomy, we have an artery, right? This artery comes by and it brings blood to a tissue, right? So that artery brings blood to a tissue, it gives you oxygen and all that kind of fun stuff. And then when that tissue is, brought when that artery has brought blood to the oxygen, the vessel is then going to leave as a vein. In a portal system, this is actually not going to happen. So in a portal system, we're going to have an artery, and it's going to bring blood to a tissue, right? However, the vein that is, there we go. The vein that is leaving the tissue is not going to go directly back to the heart like it would in the first scenario. The vein is actually going to go back to another organ. And then once that organ is done doing whatever it's going to do with it, then it's going to go back into the heart. Now you might be wondering, okay, well, what's the point of this portal system? Why are we doing this in the endocrine system? Essentially, if our hypothalamus is going to be secreting some various hormones, we don't want those hormones to enter the bloodstream, travel back to the heart, and then come all the way back around to the pituitary gland. We want the hormones that are exiting the hypothalamus to go directly into the anterior pituitary so that we're not missing anything, our hormones are not getting degraded at all, and they're being able to be implemented immediately. So here we can kind of see this is what's occurring. So this is the artery in the example that I drew down here. It's entering the hypothalamus, and instead of immediately leaving again and going back to the heart, it's first going to make a pit stop down into the anterior pituitary gland, and then it's going to leave, going all the way down. So in this class, specifically in Bio 211, we're actually going to see a lot of portal systems, 3 to be exact. So this is your first introduction to the hypophyseal portal system. Later on, we'll go over the hepatic portal system, which is an incredibly important pathway. And then we'll also go over the renal portal system. But for now, this is your first introduction to a portal system. Pretty fun. Alright, so right along here we have the anterior lobe, and we have a lot of different hormones that are getting produced from it. So, in general, easiest way to kind of remember the hormones that are all being produced here is going to be the acronym FLATPEG. And you'll see that each of the letters refers to one of the hormones that you're going to have to focus on. And I'll kind of come back to this FLATPEG acronym when I go over the Word document and show you the hormone summary chart, which is going to be your basically holy Bible for this first exam on endocrinology. And then taking a look at the E, just so you guys aren't confused later on, the E actually stands for endorphins, which you're not really tested on, so the only reason I included it was just to make the acronym seem a little bit smoother. So FLATPEG in general, just the E is endorphins. Also, the pars intermedia is referred to as the middle region, basically this dividing region right about here that's separating the anterior and posterior pituitary gland. This is known as the pars intermedia, which actually creates melanocyte stimulating hormone. And if you guys remember what melanocytes do, they increase the melanin in the epidermis. Part of the posterior lobe is those 2 hormones we talked about, is ADH and oxytocin. And I'll kind of come back to ADH in just a bit when we start talking about aldosterone a little bit, because I kind of want you to go over how they kind of interact with one another. But in general, hormonal effect of ADH is going to be the reabsorption of water and increasing blood pressure, increased BP. And then oxytocin is just going to be labor contractions, milk ejection, basically everything for birth. It's also used in males as well. Alright, so the pineal gland. The pineal gland is essentially a small little region on the posterior side of the brain that is known for synthesizing the hormone melatonin. So you want to think of melatonin as the hormone that tones it down. This is the hormone that is going to essentially put you to sleep. And what's actually cool, just a side note, is that this pineal gland is actually directly connected to some level of our optic nerve. So it actually evaluates like how much light we're seeing from over here. So if we're seeing like a lot of light, then this pineal gland is like very inactive. But if it starts to get very dark, you start to get more tired because the pineal gland notices it's dark and it wants to start producing that melatonin. Taking a look at the thyroid gland. So the thyroid gland is a small little organ found in the anterior side of our neck. So thyroid actually translates from the Greek, which refers to a shield. So the thyroid gland actually looks kind of like a shield in this aspect, a Greek shield at that. The thyroid gland is primarily in charge of your metabolism. So it's actually going to be secreting 2 different hormones, T3 and T4. And these are the only hormones that are going to require iodine to function and to increase cellular metabolism. So whenever you think of your metabolism, you're thinking of thyroid gland. That's directly in charge of it. Now, something else I should kind of bring up is that we talked a little bit about the negative feedback earlier. So if we're taking a look at the anterior lobe of the pituitary gland, the anterior lobe of the pituitary gland actually has a production of a hormone known as thyroid stimulating hormone, which is going to target our thyroid gland. And that's actually what is going to increase T3 and T4. There's a lot of different clinical correlations that come along with this. There's hypo and hyperthyroidism. So hyper and hypo. If we're just looking at this singular prefix right here, hyper refers to elevated, hypo refers to beneath. So hypothyroidism, we are producing insufficient levels of T3 and T4. There is not a lot going on. Some symptoms include weight gain, decreased body temperature, all kinds of stuff. So it's also important to note that, especially for Bio 211, there are a lot of clinicals and a lot of pathologies that we're kind of going to talk about. However, this class is just primarily focused on anatomy and physiology. We're not a patho class. Which, if we were a patho class, I would focus a lot more on what goes wrong. I just like to bring these up because sometimes it's an easier way to remember things, or it's a lot cooler to kind of connect it to a real life scenario. But that being said, I won't ever really quiz you or test you on pathologies unless I give you sufficient information, like in the question. So if I ask you a question, if I said something about Cushing's disease, and I said it's not producing, or Cushing's disease does not produce this hormone, like what would you expect to see? That will kind of be more so along like the lines of like a fair game. Alright, so the thyroid gland actually produces one additional hormone known as calcitonin. So I know you guys are familiar with calcitonin. Calcitonin is going to lower the blood calcium levels. And the way it's going to do this, it's going to inhibit osteoclast, which breaks down bone, and it's going to stimulate osteoblasts, which is going to build bone. That's primarily what I want you to focus on, is those osteoclasts and osteoblasts again. But overall, you guys should be pretty familiar with calcitonin from Bio 210. So this is a good example of the thyroid gland producing calcitonin. So let's start down here. We have homeostasis. Oh yes, we are wonderful. We are happy. There's nothing going on. Oh no, homeostasis is disturbed. We have increasing calcium levels in the blood. Maybe you're drinking too much milk. I don't know. Either way, the body does not like it. So the thyroid gland says, "Halt, stop right there. We're going to produce some calcitonin." Calcitonin is going to say, "Hey, kidneys, I need you to start getting rid of calcium. All right, we got too much going on over here. This guy decided to drink a whole bowl of milk. It's just ridiculous." Calcium deposition in bone, so your osteoblasts are going to start building more bones, and your osteoclasts are going to stop breaking down bone. Once that all happens, homeostasis restored. Our blood calcium level has dropped. And we're back to homeostasis. Alright, on the opposing side, we have the parathyroid gland. So para refers to around, and what are we around? We are around the thyroid gland. So the parathyroid gland are these four small little balls that are found on the posterior aspect of the thyroid gland. And what they're going to secrete is a hormone that's actually fairly easy to remember, is PTH. So that's going to be parathyroid hormone. And this is going to do the complete opposite of calcitonin. It's actually going to increase our calcium blood levels. So this is actually a very important key that I kind of want you guys to pay attention to in terms of studying smarter rather than studying harder. In case you haven't noticed, a lot of these hormones are antagonistic to each other, which means that they do the complete opposite function of each other. That actually makes things a lot easier to memorize, because then you're memorizing these in terms of pairs and groups rather than just like individual hormones. So that's honestly the best way to kind of look at this, is saying, oh, okay, if my body has too much calcium, I can do calcitonin. But what if another scenario occurs where I don't have enough calcium? So in this scenario, let's say, oh, well, yes, we're at homeostasis, and then all the way down here, oh, I forgot to eat my cereal this morning, so now I got decreasing calcium levels in blood. This is not good. But then the parathyroid gland, he's like a superhero. He comes in here and he says, don't worry, I'm going to secrete PTH. And this PTH is going to tell, hey, kidneys, hold on to that calcium. We need it. Our body is being dumb. We need more calcium. Calcium is released from the bone because your bone holds a lot of calcium. Hopefully you guys are aware of that. And then there's increased calcitriol production. Basically, vitamin D from the sun is going to produce more calcium and being absorbed by the digestive tract. That's a little bit more complicated, but the idea is more calcium. That is the general idea. More calcium, please. Homeostasis is restored, and we are happy again. The thymus. So, I'm not going to focus too much on the thymus at the moment, but the thymus gland is a gland found in the anterior chest wall of children mostly. So the thymus gland is actually really important for the development of T lymphocytes. So T lymphocytes are your white blood cells, or at least some of your white blood cells. They are super important for fighting viral infections, and the reason that we have a large thymus gland in children rather than adults is because children are still building up their immunity, so they still need to be developing and maturing their white blood cells, whereas adults actually have a very diminished thymus gland. So if we're actually going to take a look at the cadavers, thymus gland is nowhere to be seen. It's completely gone because, you know, they're much older cadavers rather than children. But we're not going to focus too much on what the thymus gland does at the moment. We're actually going to come back to this when we talk about the lymphatic system. The pancreas. Oh boy, you have probably heard plenty of the pancreas. That's going to be this large snail-like structure right along here. So the pancreas is actually an endocrine and an exocrine organ, which means endocrine means like it's producing hormones that go through the bloodstream. Exocrine actually means that it's going to produce another product that's actually going to fill in through this duct right along here. And this kind of is going to get later on when we talk about digestive system. But for now, we're going to focus on endocrine. So this pancreas secretes insulin and glucagon. So insulin is going to decrease the blood glucose level. So we have glucose naturally kind of flowing around in our blood. Insulin is going to say, hey, get that glucose, put it in some cells. We have too much going on in the blood. Versus glucagon is actually going to have the opposite effect. Glucagon is going to increase the amount of glucose that is found in the blood. Your body says, hey, we don't have enough glucose in the bloodstream now. Glucagon is going to kind of come in and settle that debate. And what's actually kind of interesting is that the pancreas is in charge of producing both insulin and glucagon. And it's actually done through two different types of cells. Let's see. Okay, I guess I'll discuss them here. So, the glucagon is actually going to be secreted by our alpha cells, and the insulin is going to be secreted by our beta cells. So I'll kind of go over this again when we talk about it on the Word document, but for now, just make sure you guys understand the association that beta cells are secreting insulin, insulin brings glucose blood levels down, and then the alpha cells are producing glucagon, which is going to increase the blood glucose levels. Oh, it does mention it. Beta cells secrete insulin, alpha cells secrete the glucagon. So, some more clinical correlations. Diabetes mellitus. So, diabetes mellitus, this is the type 1 and type 2 diabetes. Essentially, there is hyperglycemia. There is too much glucose in the blood constantly. And you might be wondering, okay, well, why is this the case? That's because we actually have two different causes here. So in type 1 diabetes mellitus, this is actually due to a genetic factor. So children who are born with diabetes mellitus, they don't have any receptors on their pancreas. So essentially their pancreas is blind. The pancreas can't tell, oh, there's abnormally high glucose levels. It doesn't understand that. So it's simply not producing enough insulin to keep up. Versus type 2 diabetes, this is more of an environmental factor rather than genetic. If you are constantly eating a lot of sugar, a lot of stuff that's not good for you, that's increasing your glucose levels dramatically, your cell receptors of the pancreas is actually going to decrease in terms of like your pancreas won't be able to keep up with the insulin, so then you can develop type 2 diabetes. What's also kind of funny is that mellitus actually translates as sweet. So the reason why they call it sweet is because back in the day, before they had, urinary analysis and all kinds of fun stuff, you could just taste the urine of a patient, and if it tasted sweet, it tasted like it had a lot of sugar in it, they had diabetes mellitus. So it's a little fun history fact for you. Oh, and then type 2, non-insulin dependent diabetes, most common form. This is associated with obesity, kind of some of the stuff that we kind of talked about. Insulin resistance. There you go. That's a good word right there. All right, so the adrenal glands. Now, the adrenal glands are these cute little organs that sit on top of your kidneys like a hat. Now, your adrenal glands are actually going to be split into a few different regions. So first up, we have the adrenal cortex and the adrenal medulla. So if we're going to translate these directly, this actually helps out a lot. Cortex actually translates as shell. There we go, shell. Versus medulla, which translates as like a pit or like a soft middle. So the adrenal cortex is referring to the outer portion, the more superficial portion on the outside, versus the adrenal medulla is the small little pit that's kind of found on the inside, or like right about there. Now, unfortunately for you guys, this adrenal cortex is actually going to split into 3 additional layers. And yes, you are going to have to know each layer, and you are going to have to know each hormone coming from each layer. So let's get into it. Oh, here's another kind of look. The capsule just refers to like the outer fibrous connective tissue that's kind of holding it all together. Then we can see the cortex and medulla. So, adrenal cortex, we have 3 different regions: the zona glomerulosa, the zona fasciculare, and the zona reticularis. So, an easy way that I like to remember is whenever I think of adrenal glands, I always think of, you know, your fight or flight kind of mechanism, and we're going to talk a little bit about that, but your adrenal glands usually represent a fight or flight mechanism, at least for me. So, what I like to think of is I like to think of go, fast, run. So, I like to think of go, fast, run in terms of the way that our adrenal cortex is divided into the 3 different regions. And this is actually going to work from superficial all the way to deep. So the zona reticularis is going to be our deepest region, and then the zona glomerulosa is going to be the most superficial. So the zona glomerulosa, this is going to produce mineral corticoids, and this is going to be specific for aldosterone. Now, essentially what aldosterone does is it's actually going to increase our blood pressure as well through a slightly different mechanism. So this is kind of what I wanted to get into when we're talking about the differences between ADH and aldosterone. I'll just call it ALD. So ADH is going to increase the blood pressure by increasing our water retention. So we're going to have more water kind of enter back into our system. And ADH is kind of forgot to bring this up earlier, but ADH, anti-diuretic hormone. Diuretic refers to urine. So anti-diuretic hormone refers to, you know, the lack of production of urine. So it's essentially increasing blood pressure by not excreting urine, essentially. What's actually kind of interesting is that if I don't recommend this, but if you were to drink alcohol, you know, you're over the age of 21, you decide to drink alcohol actually inhibits this ADH. So you may have noticed that somebody who's drunk may have to urinate a lot more often, because it actually inhibits ADH, which increases the production of urine. But that's just a little side fact. Back to this, ADH increases blood pressure by increasing the amount of H2O in the body. Aldosterone, however, is also going to increase the blood pressure, but it's going to do it by increasing the amount of salt that we're taking in. So this is our sodium. We're going to have more sodium entering the bloodstream, and this is actually going to also affect our H2O, which is going to follow the sodium because of osmosis. Hopefully you guys are still familiar with that term, osmosis. So this sodium is going to enter back into the bloodstream, and then the osmosis is going to pull the water back in as well. This gets into a little bit of plasma osmolarity, but I'll leave this here. I just want you to focus on this difference at the moment. Plasma osmolarity gets a little confusing, and I'm sure you guys will go over that in lecture. But back to my original point. So if we okay, you know that word says mineral right under the red stuff, but mineral, you want to think of mineral as in salt, right? Because salt is a mineral. So mineral corticoids is referring to the aldosterone. Zona fasciculate is our glucocorticoids, and this is going to be cortisol. So cortisol is also known as our stress hormone. This is an anti-inflammatory hormone, and this is actually going to produce more glucose through a process known as gluconeogenesis. Now that's a big word that comes up a lot in biochemistry, and I'm going to leave it just there. But I just wanted to introduce you guys to the idea of gluconeogenesis. Essentially, cortisol is going to be creating new glucose through a stress level mechanism. It's also anti-inflammatory, which means it's going to stop white blood cells from basically filling up an area. So if something is inflamed, you can actually give cortisol to kind of like reduce that inflammation. And then finally we have reticularis. Reticularis produces androgen, and androgen is essentially a male steroid-derived sex hormone. Oh, here we go. Aldosterone, sodium ions, salt receptors, drop-in innate. Yep, all fun stuff. All pretty much we talked about. Glucocorticoids creates glucose synthesis, basically also creates more glucose. Anti-inflammatory effects, so inhibits white blood cells. ACTH is the promoter of this product. So ACTH is a hormone from the anterior pituitary gland that we'll cover in just that we previously covered. And then androgens is pretty much just making that testosterone. Now, finally, we've gotten to the middle. So I know we talked a lot about the different regions of the adrenal cortex, and now we're looking at the adrenal medulla. So this is the pit. This is the deepest layer. Contains two types of secretory cells. One produces epinephrine, or also known as adrenaline, and the other produces norepinephrine, or noradrenaline. And do you remember when I talked about the nervous system? Well, this is what I'm talking about now. The sympathetic division of the autonomic nervous system. So that's referring to our fight or flight response. So the sympathetic nervous system is going to directly stimulate our adrenal medulla. So let's say this is our adrenal medulla, and this is the spinal cord. We actually have neurons that actually travel all the way directly to the adrenal medulla and stimulate the cells directly there. And this is going to secrete epinephrine and norepinephrine. Now, all you need to know about epinephrine and norepinephrine is it's going to increase our fight or flight response. So you kind of want to think about different parts of your body that how they would respond to a stressful situation. An example would be like your eyes. Your eyes are obviously going to dilate. They're going to get bigger so you can see more, so you can avoid danger, increase for a fight. It's going to increase your heart rate. It's going to increase your breathing capabilities, so it's going to have bronchodilation. It's going to increase the blood that's traveling to your muscles, and it's going to decrease the blood traveling to your stomach and everywhere else, because you obviously don't need to digest right now. You're in the middle of a dangerous situation. Now, there is a slight difference between epinephrine and norepinephrine by attachment of a methyl group, but that gets kind of complicated, so we're going to just leave it as these guys are both pretty much doing the same thing. They're both increasing our fight or flight response. Many other organs have a few different kind of productions, and let's see. So for the digestive system, we're going to come back to this later on in the semester. But the rest of these are pretty much fair game. So kidneys are actually going to secrete calcitriol. We already heard about that. But EPO, so this is actually known as the erythropoietin. So we're going to kind of ignore the enzyme renin for a bit. We're going to come back to that during the urinary unit. But EPO, erythropoietin, basically this stimulates for the kidneys to produce more blood cells. So I'm just going to leave it at that. EPO produces more blood cells. Now, the heart cardiovascular system is going to produce two different hormones known as ANP and BNP. This stands for atrial natriuretic peptide and brain natriuretic peptide. Essentially, what both of these are going to do, they're going to decrease blood pressure. So we've talked about the different hormones that are capable of that are capable of increasing blood pressure. But like I said, you kind of want to think of these hormones as antagonistic to each other. So if you have one hormone that does one action, think of what hormone would do the opposite action. And in this case, ANP and BNP secreted by the heart are actually going to decrease that blood pressure. You might be wondering, oh, why is it called brain natriuretic peptide? Basically, back in the day, scientists first discovered BNP in the brain, so they thought the brain directly was producing it. That has since been disproven. However, scientists are lazy, so we're going to keep calling it BNP, even though it's not coming from the brain, it's coming from the heart. Next up, gonads. So gonads refers to your reproductive genitalia. Our ovaries, or more specifically, not my ovaries, but probably somebody else's, are going to produce estrogen and progesterone. So we'll get a little bit into the differences between estrogen and progesterone later on down the line when we talk more about the reproductive reproductive anatomy. But in the meantime, testes are going to produce testosterone. So this is for the male, this is for the female. And then finally, we have adipose tissue. So I'm going to bring this up briefly. Adipose tissue secretes a product known as leptin. So what leptin does is it's going to essentially decrease your appetite. So adipose tissue is referred to as your fat tissue, right? It's a storage of energy and insulation and heat and all kinds of fun stuff. So this is going to decrease your appetite. It's going to say you are full. Discard that real quick. Okay, so we've gone through pretty much a lot of different hormones here. However, we're not done quite yet. We're actually going to take a look at some of the histology slides. So a large portion of your quiz and exam for endocrinology is also going to be taking a look at your histology slides. And let's go ahead and let's go ahead and get through some of them on this PowerPoint. Come on, here we go. All right, so we talked a lot about that. Talked about that. Ah, wonderful. Pituitary gland. So this is the hypophysis. Now, this is not a very pretty picture, but this is the picture that we're working with. Now, we have the adenohypophysis, which is the anterior pituitary gland. Easy way to remember that is adeno starts with A, and so does anterior. So adeno-anterior hypophysis, or pituitary gland. And then the posterior, that's with the direct neuronal development, so that's the neurohypophysis. Now, you might be wondering, okay, well, why do these look like this? So you're not always going to have a brain that has, the left side is anterior, the right side is posterior, etc., etc. We actually have to notice the difference in colors, and that's going to be the easiest way to identify the different lobes of the pituitary gland. Now, the reason why the neurohypophysis has this very distinct, whitish matter is because of the neurons. The neurons are giving this white matter kind of look, versus this much darker purplish color in the adenohypophysis because of that hypophyseal portal system. The hypophyseal portal system is bringing a lot of blood to the anterior pituitary gland. So all of this kind of darker color you see right here is because of that blood from that portal system. Here we can see the neurohypophysis and adenohypophysis once again. Neurohypophysis has that white matter of that neuronal stuff, and then adenohypophysis is all the extra blood. Don't worry too much about identifying the pars intermedia. I'm unlikely to test on it, but other than that, here's the rest of it. There we go. Thyroid gland, perfect. So, taking a look at our thyroid gland, I want you guys to first notice this huge colloid. So these huge colloids are these big open spaces found in the centers around the simple cuboidal epithelium that are kind of surrounding all around here. These follicular cells are simple cuboidal epithelium that surround the colloid. This is actually what's going to be producing that T3 and T4 through a very complex mechanism that you're likely to kind of get covered in your lecture portion, but we're not going to go that far. I just want you guys to recognize the colloid and the follicular cells that secrete T3 and T4. I also want you to notice the parafollicular cells. So the parafollicular cells are actually found along the outside portions that are not in direct contact with the colloid. These are also known as C cells. And these parafollicular cells, or C cells, are actually going to produce calcitonin. So you can kind of see the difference now. The colloid and follicular cells, they work together to create T3, T4. The parafollicular cells, they have their own region and they're going to be creating calcitonin. Taking a look here, you might recognize, oh, it's a colloid, and that's follicular epithelium. So we must be in the thyroid, and you would be correct. However, there's a more specific region. We're actually on the posterior side of our thyroid gland. So while these do look familiar, you might also notice this humongous structure over here. This is actually our parathyroid gland. And don't worry too much about distinguishing the individual components of the parathyroid gland. All you really need to know is that this guy right here is producing PTH. So let's kind of break this down. We got PTH getting produced all up in here. All over here we got T3 and T4 kind of being made. And then we have our like parafollicular cells right along here that are producing that calcitonin. There we go. So, taking a look at our pancreas. Now, our pancreas has two distinct regions, right? We talked about the endocrine and exocrine portions of it. Now let's get into a little bit more detail of it. So, you can kind of see this distinct color. It kind of looks like an island, right? So, this is pronounced as the islets of Langerhans. They can also be pronounced or called the islands of Langerhans, because I want you to imagine all this over here. This is a mighty fine big ocean. And this ocean is where all of the exocrine glands are found. But on this tiny little island is where all of the endocrine production is going to be done. And so, therefore, our alpha cells and our beta cells are both going to be found in this little island of Langerhans, or islet of Langerhans. Once again, you can see the islands that we have where our alpha and beta cells are coming from. And then we have our ocean surrounding our islands. Alright, so taking a look at this, this is actually going to be our adrenal gland. Now, when it comes to test day and quiz day, I'm going to be very distinct about my arrows. So I'll point out like the 3 different regions or 4 different regions with an arrow or with a sticker, but maybe only ask you for one of the 4. So over here is going to be the capsule region. So it's going to be the most superficial portion. That's going to be in contact with the outside world. So hopefully you guys remember the mnemonic of go, fast, run. So you can kind of see the distinct little differences that are kind of occurring right along here. There we go. So the zona glomerulosa is going to be our mineral corticoid producing region. So this is going to be our most superficial region. The next region, you can kind of see the distinct difference in color as we transition from, let's see, how would I describe this color? Magenta to pink. Let's call that magenta to pink. I don't know. I'm partially colorblind, so this also doesn't really help out too much. But yeah, so we also have zona fasciculata, and then this is going to be our glucocorticoid producing region. That's where the cortisol is made. And then zona reticularis is going to be the androgen region. And then finally, probably the easiest region to identify is this distinct deep purple region over here. So this distinct purple region is going to be the medulla. So the adrenal medulla. Come on now. And then once we actually pass the adrenal medulla, we are back over to the zona reticularis and then zona fasciculata again. So this is kind of like a shell, when you think about it, like that. And then we're actually just kind of cutting right across it. So this is like the distinct region we took out of it. Here you can kind of see a lot of different pictures in your textbook as well of how it's divided up. Thymus, don't worry too much on this thymus. I'm not going to focus too much on it. All right, so that covers all of the histology portions that you need to know. Let's see. Looking at the Word document, this Word document right here is amazing. This covers every single major organ that's producing hormones that you need to know, all of the hormones, and then all of their effects as well. So as long as you are studying this, you are rock solid. At least for my quizzes and my exams. So hypothalamus, if you notice here, a lot of the hormones that the hypothalamus is secreting are going to start with the name releasing or inhibiting. That is a big kind of factor about how, or like which hormones are coming from the hypothalamus. If it says something releasing hormone, something inhibiting hormone, that is coming from the hypothalamus, because the hypothalamus again does not talk directly to the workers, because he's big shot CEO, so he tells pretty much all of these hormones, these releasing and inhibiting hormones, are going to go down to our anterior pituitary gland. And you can kind of see that pretty much the only target that the hypothalamus focuses on is the anterior pituitary. Whereas the anterior pituitary has the flat pig. So here's our follicle stimulating hormone. That's the F. Luteinizing hormone is the L. A is the adrenocorticotropic hormone. So this may sound a little complicated at first, but if we break down that word, adreno is referring to adrenal. Cortical is referring to the cortisol. So the adrenal cortical tropic is referring to the hormone that's going to be targeting our adrenal gland, and more specifically the zona fasciculata. We have so that's FLAT is going to be our thyroid stimulating hormone. We talked a little bit about thyroid stimulating hormone to secrete T3 and T4. Or then we have flat peg. So P is going to be the prolactin. Prolactin is going to be essentially for milk production. E is endorphins. Like I said, don't worry too much about endorphins. And then G is growth hormone. So growth hormone is for your muscle, bone, liver, all that kind of fun stuff. Melanocyte stimulating hormone. The reason why it's not really a part of the flat pig is because technically the MSH is coming from the pars intermedia. So that's the region between the anterior and posterior pituitary gland. Let's go ahead and keep it that way. So the MSH is coming from the pars intermedia, not the anterior pituitary. I just want to make that distinct note for you guys. Oxytocin and ADH. Another term that's actually really good is vasopressin. The reason why there's actually two different names for this hormone, antidiuretic hormone and vasopressin, was actually kind of a funny story. Two different groups of scientists were studying the effects of a hormone at the same exact time, and they both found similar effects essentially between this ADH and vasopressin, and then they realized they were studying the same hormone, but neither of them wanted to give up the naming of it, so now we had to call it both. So that's nice. You can see here for regulation, the plus sign refers to being stimulated by versus the negative is inhibited by. So like I said, your vasopressin or antidiuretic hormone is suppressed by alcohol, so it makes you create more urine. There's your thyroid, adrenal cortex, adrenal medulla, pancreas, ovaries, testes, heart, kidneys. We're going to stop it right about here. So all of these hormones, minus leptin, are not going to be on your first test, because your stomach cells, your duodenum, your small intestine, placenta, this is all stuff that we're going to be covering later on in the course, and I think it's more appropriate that we bring it up in its actual full context rather than a shortened summary that's kind of shown here. So pretty much you can kind of cross off all these hormones that are down here underneath kidneys besides adipose tissue leptin. But all right, that is the end of the video. I hope you guys had a good time watching, and I will see you guys later.